Welcome back, people, to another Rock the JVM video. I'm Daniel, and in this video I'm going to talk about lenses, prisms, and optics in Scala. In this video I'm going to use the Monocle library for Scala, and I'm going to discuss the optics principles that it's based upon. So this video will assume that you know some essential Scala, obviously, and you're a big fan of the don't repeat yourself principle because Monocle solves this problem for a particular use case. Now, as always, I'll recommend that you code with me in this video, and whenever you need to refresh your memory, just refer back to this video or to its written form at rockthejvm.com/blog with the link in the description. The link will also contain everything that we are going to discuss in this video, including the library definitions. So with that said, let's get back to our code editor. I've just created a simple object here with a main method in case we need to test anything. And for this video, I'm going to use the Monocle library. So if you go to your build.sbt file, you can use the Monocle core and Monocle macro libraries from GitHub Julien Truffaut, who is the developer of the main contributor of Monocle, and I'm using the Monocle version 2.03 at the moment of this recording. It seems to be either the latest or one of the latest, and I'm going to add this definition to the description in this video so that it's easy for you to include it into your build.sbt. The article at the blog will also contain this as well. So let's get back to our code and let's discuss what kind of problem Monocle solves. So Monocle was invented because nested data structures are a pain to inspect and change. And the pain increases with the depth of the data structures. So consider the following scenario. Assume we are designing an online web portal, like a Wikipedia or a web compendium of rock bands, right? Where Rock the JVM, right? So we're thinking about following this data structure design. I'm going to define a case class called guitar with a make as a string and a model as a string. And I'm going to define a case class called Guitarist with a name as a string and a favorite guitar as a guitar. Everyone has their favorite guitar. And I'm also going to define a case class called Rock Band, who has a name as a string, a year formed as an int, so the year when the band was created, and the lead guitarist for the band as a guitarist. All right, so assume we're doing a web portal with these rock bands, and we're holding an online database of guitarists, guitars, rock bands, and so on and so forth. Now, let's assume that we have created some bands for our database, and I'm going to define a val called, say, Metallica, who is a rock band with name Metallica, formed in 1981, and the lead guitarist for Metallica is Guitarist Kirk Hammett, and his favorite guitar is a guitar with the model with the make ESP, and the model of the guitar is M2 with Roman letters. Now, let's also assume that we have a giant database of guitars, for example, this thing over here, and we want to store them in a consistent format in our database. So to comply with that format, let's assume that we need to replace all spaces in a guitarist model, like here, with a dash. Okay, so we want to replace all the spaces with a dash just to comply with the consistent format in our database. Now, normally, we would have to go through this entire data structure and copy everything up to the guitarist model. So if I wanted to fix this data structure where this name of the guitar is changed to a dash, I would say something like this. I'm going to say Metallica fixed as Metallica dot copy, and I would copy the lead guitarist. So I'm going to say lead guitarist equals, and I'm going to say Metallica lead guitarist dot copy again, and I'm going to copy Kirk, and his favorite guitar is going to be Metallica lead guitarist favorite guitar copy, and the model here is going to be Metallica lead guitarist favorite guitar model, and then I will need to replace all spaces. So replace the space with a dash. So just to be able to replace the name of the favorite guitar of Kirk Hammett, I would need to copy every single intermediate data structure so that I get the proper band again. So this is a pain. Imagine that we have many places in our app, in our online database where we would have to do this. The code would be a mess to be able to comply with this format for every single piece of code that we might need to in our application. So this is where the Monocle library comes in. So Monocle gives us the capability to access a deeply nested field in a data structure, inspect it, or change it at will, therefore creating a new data structure as a result. So here's how we would do this particular use case, replacing the name of the guitar with a dash by using Monocle. So I'm going to start very easy. I'm going to say val, let's call this Kirk's fav guitar as guitar with the make ESP and the model M2, just to show you how it would work. Now, in order for us to replace this particular field in the guitar data structure, I would need to import monocle.lens, and I'm going to also import Monocle macros genlens, and I'm going to probably spell import, and I'm going to use the following code. First, I'm going to define a lens, and I'm going to explain what that is in just a second. So I'm going to say guitar model lens as a lens which takes two type arguments: the initial data structure that I'm inspecting, guitar, and the type of the field that I want to inspect, which is in our case a string. And I'm going to use on the right hand side genlens with guitar. And whenever you write genlens with a guitar, you will need to access the field of a guitar which is of type string. So I'm going to use _.model. Now, genlens here is based on a Scala macro. There's a lot of magic that's happening behind the scenes, and I'm going to explain what the effect of doing that will be. So once I have a lens, I can use this lens to access the field of a guitar instance. So if I want to inspect a field, I would use this lens to zoom into the data structure that I'm interested in. This is why it's called a lens. So I'm going to say val, let's call this Kirk's guitar model as guitar model lens dot get, and I would need to pass in the initial guitar. So I'm going to say Kirk's favorite guitar, and by calling get, I would inspect this data structure and I would return whatever the lens is designed to obtain, in our case the model of the guitar, and this will return the string M2. So notice that we are using the get field to inspect a data structure using a lens. If you want to modify a field, I would simply say, let's call this formatted guitar as guitar model lens dot modify, and the modify method takes a function from string to string, in our case _replace, and I replace the string space with a dash. And then as a second argument list, I would need to pass in the actual guitar whose field I want to replace, and I will pass in Kirk's favorite guitar. Now this expression over here will return another guitar whose field described by this lens will be replaced with this function. So this will be a guitar with the model ESP and the model M-2. Now in main, if I print this formatted guitar, so print line formatted guitar, and if I run this application, I'm going to see this exact data structure. So guitar ESP with M-2. So I hope you get the picture. A lens is able to zoom into the field of a data structure. And in this case, this code has the same utility as simply accessing a field or copying a case class instance, because this case class has a simple field of type string. Now the power of these lenses will become apparent when we compose them. So I'm going to define some further values. I'm going to define, let's call this lead guitarist lens, that given a rock band, I'm going to access its lead guitarist. So I'm going to say gen lens with rock band and I'm going to say _.leadGuitarist. So this will be a lens that, given a rock band, actually I'm not even going to type it, I'm going to show you what IntelliJ actually infers. So lead guitarist lens is a lens that, given a rock band, will return a guitarist instance. Look at that. Now, given a guitarist, I should also be able to access its favorite guitar. So I'm going to say val, let's call this favorite guitar lens as gen lens, that given a guitarist, I'm going to say _.favorite guitar. Okay, and I also have the guitar model lens that I've defined before. Now, if I want to inspect the guitar model of the favorite guitar of the lead guitarist of a rock band, I can simply compose these lens, let's call this composed lens, as lead guitarist lens. That is the first lens that takes a rock band and returns a guitarist. And I'm going to say composed lens. And I can add another lens here. So I'm going to say guitar lens, or favorite guitar lens. So this takes a rock band and returns a guitarist. This takes a guitarist and returns its favorite guitar. And then I can compose this further. And I can pass guitar model lens. And this lens is able to zoom into a rock band. And this is actually a lens of rock band and string. So this lens is able to zoom very deep into a rock band and extract or inspect the favorite guitar model of their rock band's lead guitarist. So I can zoom in as deep as I want. And with this lens, I can follow the same pattern that we followed above in the simple case and just do the following. I can say, let's call this Kirk's guitar model 2 as composed lens dot get, and I need to pass in the rock band. So I'm going to say Metallica. If I pass in Metallica, this lens is able to zoom very deep into the Metallica rock band, and it can return the favorite guitar model of their lead guitarist. So I'm going to print line Kirk's guitar model 2, if you're curious to see how that would look like. So notice we have M2 here, and we can also change it by using the same modify pattern. So I'm going to say, for example, Metallica fixed 2 as composed lens dot modify, and I can pass in a function from string to string, and I can say _replace, and I'm passing the space and a dash. Now, I don't need to just replace it, I also need to pass in the actual data structure that I'm inspecting, which is the rock band. So I'm going to pass in Metallica here. All right, so given a rock band, I can run this function on the field that this composed lens is able to access, and I return a new data structure. So if I print line Metallica fixed 2 here in main, and if I run this, you will see that the Metallica band has been changed. So we have rock band with Metallica, 1981, guitarist Kirk Hammett, and guitar, ESP, and all the way down we have the changed data structure M-2. Now, even though we created a bunch of lenses here, which is still 3 lines of code as we did earlier with copy, now this lens is reusable throughout your entire application. So the lens is reusable, and you can inspect or get or modify and so on and so forth in every piece of your code where you would need to do that. So without needing to follow this very ugly copy pattern above. So you do it once, you create this lens once, and you can reuse it everywhere, therefore following the dry principle. Now, I'm pretty sure you understand why this pattern is called a lens now, because it allows us to zoom into deeply buried fields of data structures and then inspect or modify them right there. Now, the second thing that I want to show you is prisms. And this case was lenses. And the next thing that I'm going to show you is prisms. Prisms are another interesting tool for manipulating data structures. Now, this time we're working in the world of hierarchies, usually sealed classes or traits or enums. here's a scenario. Let's assume that we're working on some kind of visual design app, and we have various built-in shapes in place. So we can design logos and brands and so on and so forth with shapes. And we'd like to be able to manipulate their features while still working against the main interface. Here's what I mean. Let's say we have a sealed trait, let's call this shape, and we have a bunch of case classes that extend it. So I'm going to say case class, let's call this circle with a radius, which is a double, and this extends shape. Let's assume we have a case class, let's call this rectangle, with a width as a double and a height as a double. This also extends shape. And another case class, let's call this triangle, which has three sides of the triangle, A double, B double, and C double. This also extends shape. And for triangle, you would have to do some assertions here because not every combination of three double can describe a triangle. So from a mathematical, geometrical perspective, you would need to do some assertions here. For example, the first side needs to be bigger than 0 and less than the sum of the other two, and vice versa for the other tuples as well. But I'm going to keep this super simple. All right. Now, I'm going to create a bunch of shapes here. So I'm going to define a circle as circle 20. I'm going to define a rectangle, which is rectangle, let's say 10 and 20. And let's call this triangle, or a triangle, as a triangle with some sides. I'm going to use 3, 4, 5 because these follow Pythagoras theorem. And I'm going to define a shape, which is of type shape. So I'm going to use a little bit of polymorphism here. I'm going to say that this shape is actually a circle. Okay, so this is declared to be the top level class, the top of the hierarchy, the shape class, but in fact I'm using the polymorphism, and on the right hand side I'm actually using a circle here. Now in this scenario, we would like to be able to increase the radius of this shape, which is a shape. And we would like to increase its radius if it's a circle, or leave it intact otherwise, and all without having to resort to type checks. So of course, we can do things like if a shape is instance of circle, and then we would, I don't know, change the radius. But is instance of checks are usually pretty obnoxious, so you won't see this in good quality code. We can also do pattern matching, so we can say val new circle of type shape as shape match, or a shape. That's how I defined it. A shape match, in the case that we have a circle with a radius, I'm going to return another circle with r plus 10, for example, and leave it intact otherwise. So in case I get a shape, I just return that. But the point is that whenever you need to apply this function or this modification to a shape that is declared to be the top of the hierarchy, you would need to resort to either type checking or pattern matching every time. So you would need to repeat yourself all the time. But again, if we wanted to apply this transformation to many shapes without various parts of our code, we have no choice but to repeat it. So enter prisms. So here's what we can do with a little bit of nice optics. So I'm going to import monocle.prism. I'm going to describe what a prism is, and the construction of a prism is a little bit more complicated, but hopefully it'll make sense towards the end of the example. So I'm going to define a circle prism as a prism which takes two type arguments, shape and double, meaning that given a shape we can extract or access its double, which means a radius in our case, and we need two functions that'll turn a shape into a double and backwards from a double to a shape. And so we would need the first argument to pattern match against the shape. So I'm going to say case circle r, I'm going to return the radius. but I'm going to return the radius as an option. So I'm going to say sum r. And in case we have something else like a rectangle, which doesn't have a radius, I'm going to return none. So the first function takes a shape and needs to return an option double. The second function that we need to pass to this constructor here is a function from a double to a shape, which is in our case a circle. So given a radius of type double, I'm going to construct a circle R. So in other words, a prism will be a wrapper over a back and forth transformation between a shape and a double. And a prism allows us to investigate a shape and get a double, or use a double and create a shape. So I can use this prism to create a shape. So I'm going to say, let's call this another circle, as circle prism applied to the value, let's say 30. Whenever you say circle prism applied to the value of 30, you can think of this application as some kind of a smart constructor. Because the declared type is a shape, so notice here another circle is a shape, but in fact, because of the construction of the circle prism, the returned object will actually be a circle by this function. Now, if you want to access some shape's radius using this prism, I'm going to define, let's call this radius, as circle prism get option with a circle, this returns sum with the circle's radius, and in our case we'll have 20 here. So whenever you say get option, this function here will be run on the shape that you pass as argument. And in our case, because the object here is actually a circle, we will return sum 20. But if I pass in something else, like no radius, as circle prism get option a rectangle, I'm going to return none, because this rectangle is not a circle. All right, but notice that we can use get option on any kind of shape, so we don't need to type check anymore. We can simply use this get option method to return a radius or return none, depending on whether the passed object is actually a circle or not. So we don't need to do type checks or pattern matching anymore. We don't need to repeat ourselves. So notice that we can now reuse this prism either to construct shapes or to inspect shapes. We never make any assumption of whether a shape is actually a circle or not. We can program against the bigger interface, the shape, but the prism has its internal logic that you can reuse inside your applications, therefore following the dry principle again. Now, why is this pattern called a prism? Well, that is because we are working with a type hierarchy, which you can imagine as a prism with multiple facets, either a circle or a rectangle or a triangle or many other possible options. This is why this use case is very applicable here. So you can imagine here the type hierarchy as being a prism and just looking through one of the facets that you care about, in our case, a circle. Now, this prism, not only is it really powerful because it allows you to not repeat yourself and just reuse this logic throughout your application, but you can combine that with the lens pattern that we described earlier and with a bunch of other optics patterns that Monocle supports, and get some really, really nice effects. So probably the most powerful feature of Monocle is the ability to compose these patterns and other patterns, and we can inspect and or modify nested data structures by combining the capability to zoom in, that is a lens, and to isolate a type, that is a prism. So imagine somebody is designing a brand identity with our little visual design app, which has these little data structures, and I'm going to define a bunch of other data structures here. I'm going to define combinations, and I'm going to define a case class called icon, which has a background as a string, just the description of a color, and a shape, which is a shape. And this icon is embedded into another case class. I'm going to name this brand identity. And this brand identity has some sort of logo and an icon. So I'm going to define another case class here. I'm going to name this logo with a color as a string, and this brand identity has a logo and an icon. Okay, so some nested data structure. Now, if you want to change the radius of the icon of a brand, assuming it's a circle, or leave it intact otherwise, we would create the appropriate accessors, that is lenses, to zoom into the shape's radius, and then modifiers for our desired type, in our case the circle, which is involving a prism. So here's what I would do. I would create, let's call this icon lens, to be able to zoom into this brand identity. So I'm going to say gen lens with brand identity, and I'm going to access its icon field. Then I would need to zoom into the icon case class and return its shape. So I'm going to say val shape lens as gen lens with icon, and I'm going to use underscore shape. And now I would combine this icon lens with a shape lens and with the circle prism that we defined earlier. So I'm going to define, let's call this brand circle R for radius, as icon lens dot compose lens with shape lens. So now I'm able to zoom into the shape of the brand identity, but now I can also deal with this shape as a circle by compose prism. And after I say compose prism, I can pass in my circle prism. Now, with all of these in place, we can take some brands and apply some transformations. So let me define a brand. Let's call this a brand as brand identity with a logo with the color red, and with an icon with the background white, and the shape of that is going to be a circle with a radius 45, for example. And now, with this brand circle R accessor here, I can modify the radius of this brand identity's circle icon by doing the following. I'm going to say, let's call this enlarged radius as brand circle R dot modify, and the modify method takes a function from double to double, so I'm going to say underscore plus 10. And this modification will only occur on a brand only if its shape of the icon is a circle, otherwise it will leave it intact. And because we have a circle 45, we will turn that into a circle 55 automatically. So if I print line enlarged radius, let's see what we get. So notice we have a brand identity with the same logo, an icon with the same color, but now the circle has the modified radius here of 55. If, conversely, I have a brand identity whose icon has a shape of another kind, for example, a triangle, then that shape will be left intact. And let me give you an example. Let's call this a triangle brand as brand identity with logo yellow and icon, let's say the background is black, and the shape is a triangle with 3, 4, 5. And I want to run the same transformation. So I'm going to copy this, and I'm going to name this enlarged radius triangle, which doesn't really make any sense because this triangle brand has a triangle icon. But if it doesn't make any sense, then the data structure will be left intact. So I'm going to use a triangle brand here, and I'm going to print the result to the console. So enlarged radius triangle. And if I run this application, I should be seeing the same data structure left intact. So we have a brand identity with the same logo and an icon with the same background, and the triangle with the same data, 3, 4, and 5. So notice that this logic over here, to be able to zoom into the field of a data structure and to be able to manipulate it only if it's a circle, can be safely reused inside your application wherever you need it without needing to resort to copying case classes and pattern matching as you saw here. All right. So there you have it, folks. You have the lens and prisms and optics principles in Scala with a very, very nice Monocle library. If you like this video, let me know in the comments and I will add some new and advanced lens and optics processing with some advanced topics in Monocle. So if you like this video, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this, and follow us on Twitter and LinkedIn for updates on upcoming material. Now, as always, I'm dying for feedback, so please leave your comments. I read every single one, and just check out the Rock the JVM website where we have tons of materials like this. Until next time, I'm Daniel, signing off.